and we can proceed.
Yeah, sure. I
So,
also have it in a recording, so if anyone missed anything, I will later share it on as well.
okay, thank you, Eunice. So for today's session, I'll be going over really an introduction on NLP, Kaggle, and deep learning. The session is divided up into two portions. The first portion will discuss briefly of these key components of NLP, Kaggle, and deep learning, not really going into the theoretical information regarding these details, and not really going into heavily in the mathematics. Not, I believe there's only one slide containing a little bit of math. Primarily, I want to focus on the application and looking at some code and doing some implementation and really learning through example and how we can utilize PyTorch for our very first sentiment analysis problem. So the agenda for today is I'll briefly discuss what Kaggle is, what's available in it, and really ways to succeed in competition as well as in NLP research tasks. Then we'll look into natural language processing, look at the introduction, high overview of it, really some specific tasks that's where the area of focus is within natural language processing. And then we'll also look at some algorithms that I'll introduce here primarily because it's being utilized within the implementation portion. So at least we have an understanding of the specific algorithms that we're utilizing. Then we'll look at deep learning, really the components between the supervised, unsupervised, and the semi-supervised, the key architectural components, as well as the learning algorithm. We'll provide really a general overview of the learning algorithm and keep it as basic as possible, not going into the mathematical component of backpropagation at this point. Really the learning objectives for this session is really how to navigate through Kaggle and how to utilize it fully, how we can examine and analyze a data set, specifically with data sets containing text, how we prepare and pre-process NLP data for deep learning, and really the key focus is implement and train a feed-forward multi-layer neural network for this session. So what is Kaggle? Kaggle is a subsidiary of Google. Google bought Kaggle roughly around, I believe, 2017. They're the largest online community of data science. Primarily, people know Kaggle as a computation platform. However, it's really a large community of data science that offers powerful tools and resources. On top of competitions, they hold a large database of publicly available data sets, as well as public notebooks and some introductory courses specific to data scientists. So when it comes to the competition, there's different areas when it comes to the prizes in the competitions. There's cash prizes, often hosted by some industry partner. And then there's swag, which is just giveaways and items just for participating within those competitions. But really two things I want to highlight with the competition is I find the competition is really great place when you want to look for prizes, looking at kudos as well as knowledge, where the community is very open when it comes to these type of competitions, and there's a lot of learning experience that can be gathered by reviewing some of these competitions that have a prize of kudos or knowledge. Um, Again, there's different types. There's active, completed, and in class. The active ones are the competitions that are still ongoing. The prize, the if there's a cash or swag or kudos a prize associated with that competition, the participant is still able to receive those prizes. For completed, while completed, you're not able to receive those prizes. However, you can still play around with those competitions by participating in it, submitting late submissions, and seeing really where you would place. And then in class are really small little competitions that anybody can create. They are, you can host your own competition, and upload a specific data sets, specify specific rules, and then kind of monitor the performance of potentially students competing in that competition. And for the Kaggle tools and resources, as I mentioned, there's the different competitions. The data sets, there's a rich set of publicly available data sets that is distributed through the competitions, or just standalone data sets that other community members of the data science within Kaggle upload and release it as publicly available. They really range with a variety of domains, being medical, financial, public health, environmental, etc. So it's very good in a central area with available data sets. Even the data set might not necessarily be the original origin of Kaggle, but I find it's a very nice place for consolidated repository of data sets, even for well-known data sets that's originally created by, let's say, Stanford or Google or Facebook. It's oftentimes that you'll see a copy of those popular data sets within Kaggle. And as well, those data sets range between the different modalities that they offer. The various they offer, they come in the form of text, numerical, images, as well as signals. They range between labeled, unlabeled, as well as semi-supervised labeled data. So really, there's a variety of data sets available. And I think really two areas that not many people may necessarily know about if they haven't explored Kaggle quite yet is the available notebooks and courses. Kaggle actually offers some very nice introductory courses for data scientists, providing interactive application samples through their notebooks. As well as notebooks itself are very useful, not beyond the introductory course, where a lot of times you'll see notebooks that provide some explanation of some form of state-of-the-art model that's currently being used in a specific task. So that's these notebooks are really good in learning and experimenting with these state-of-the-art models, as well as different models, where in the fact that these notebooks have already been pre-created for you, you don't need to recreate these models from scratch. It's a very good starting point, as well as there's a lot of notebooks pertaining towards people's journey towards a specific competition. So they outline, it's a bit of a journal that they outline the specific steps that the iteration that they perform during specific competitions, showing specifically outlines of codes, what they did, generating results, and then a lot of them as well. They kind of jot down their specific thought process of why they kind of uh, deviated towards a specific model and why they perform specific uh, actions due to the results that they find. So I just wanted to highlight some key ways of success. I believe that's very useful in terms of Kaggle competitions, as well as competitions uh, available that's hosted through other platforms, not necessarily Kaggle. Even if a competition is hosted in a different platform, I find it's very useful to find a very similar competition in Kaggle and kind of get a sense idea of what uh, how people kind of tackle that specific problem. So as well as this is also applicable to general research when it comes to machine learning and NLP. The very first thing is really when you look at the competition at the start of the competition is it's very good to really understand the problem task. Really identify if it's a supervised, unsupervised, or semi-supervised type of learning. Now, for anyone that's not familiar with those concepts, I'll cover. Don't worry, I'll cover that a little bit later on in this presentation as well. But as well as when you look at the problem task is get a key area that's I believe is underutilized when it comes to specifically competitions is understand the mechanics of the evaluation metric that's being used to evaluate the performance of the participants. In some area, in most cases, um, there's the specific evaluation metrics will a bit in kind of a way lead towards specifically how you approach the problem in the fact of in most cases the evaluation metrics is not a one fit all metrics that's the best for that specific task. There is oftentimes limitations to the specific metrics for the given task, even if it's the most widely used evaluation metrics for that task. And then the second component is really understand the data sets, the data set that's offered in that competition. To perform some initial analysis, statistical analysis of the distribution of the data sets, um, uh, try to identify any specific key features that is easily identifiably mappable between the feature to the intended target task is also a very good step in understanding the data sets as well as the structure of the data sets because again that really determines your approach if the data set that you're working with is text or image or a combination of both or a combination of numerical it will really dictate how you tackle those specific problems. And the third component I think is if not one of the key components, is really learn from the community when it comes to the Kaggle competitions, where there's enrichment, the rich resources when it comes to notebooks as well as discussions is abundant in the Kaggle competition. Even within that specific competitions, while the competition's going on, there is a lot of discussions that's going on with current participants and really what they're doing and having an open discussions. In some cases as well, it's discussions regarding potential limitations to the valuation metric, specific ideas towards specific approaches, and those components. And the the next 2 points really go hand in hand with get your hands dirty when it comes to the Kaggle competitions. It's really looking at the notebooks, experimenting, trial, multiple iterations of implementing a model, reviewing the results, and making the necessary modification based off of the performance that you receive and the analysis that you conduct after the model. And then it goes hand to hand with the persistence is really key in the fact that when you initially implement a model, in most cases, the results, it won't be spectacular. It's only through multiple iterations where you get good results, not only just in really the implementation of the model, the design, the design decision of the model, but as well as once really you identify a specific model that you want to focus on, there's a lot of work when it comes to fine tuning as well. So now a little bit of introduction with NLP. So NLP really originates from the linguistics. However, it shouldn't be confused with linguistics, where there are some instances of I come across people where uh, they're hesitant on working on specifically NLP tasks, where they would lean towards more computer vision, where uh, they're heavily invested in the idea that you need a good understanding of linguistics. And I just kind of provided a definition there where linguistics, based off the Cambridge Dictionary, is the scientific study of the structure and development of language in general or a particular language. So I, I know there's some hesitations when it comes to initially working with NLP tasks, where there's a hesitation uh, of worrying that you're not too familiar with grammatical or linguistic structure. However, we really focus, NLP really stems from or originates from computational linguistics, where it's really the study of the computer systems for understanding and generating language, natural language. It's more looking at from the mathematical as well as statistical perspective. It's helpful to know a bit of the grammatical perspective. However, that's where the multidiscipline really comes in afterwards to get those expert domain knowledge. And NLP can essentially be thought of within two key components: natural language understanding and natural language generation. Natural language understanding is given some form of text. How can we represent that in some statistical representation that a machine will understand? And natural language generation is how can we make a machine generate natural language. So those are really the key areas of NLP. However, oftentimes you'll kind of see in online as well as in different literature, it's kind of being used interchangeably during this time. So some specific tasks that I wanted to look at to really highlight is two areas, one being the traditional and the more modern tasks that we're kind of seeing where it's the primary focus right now. So in the traditional tasks, we have tokenization, which we try to tokenize given text in towards paragraphs or sentences or specific words. So we try to divide the given text rather being identify uh, specific paragraphs, specific sentences, or each specific word. Then we have name entity recognition, which is the task of identifying name entities within a given text. So a person's name, a place, time, those are name entities recognition. We also have part of speech, so that's identifying the structure uh, of the given word. So is the word a noun, adverb, so on and so forth. Then we have parsing, is really identifying the syntactical structure of a given text. And then language modeling is how we can represent specific documents, specific words in terms of modeling. And then the more interesting, which I think are the more interesting tasks currently being looked at right now, which is the primarily task, which are sentiment analysis, which looks at the sentiment of the given text. So is the writer of the text uh, portraying a positive outlook, a neutral or a negative perspective. And then really emotional analysis of the text, where we try to identify the emotional state of the writer writing provided the given text. Summarization is given the text, a large text, can we summarize it to a few sentences. And then paraphrasing is uh, the the rewording of specific sentence so that it maintains its semantic meaning. Misinformation detection, which is a very hot topic right now with the growth of social media and the large consumption of news being uh, consumed by uh, the population now through social media. Dialogue systems, dialogue systems is similar to chat box. These stem from uh, goal-oriented dialogue systems where there's a conversation between machine and the intention of the user is to achieve a specific goal. Um, for example, ordering ordering from a restaurant or booking an appointment would be an object uh, goal-oriented dialogue system, or just a chat box dialogue systems where it's just really an open conversation between machine and human, where uh, the machine is responding to uh, the human's responses as if it was human and maintaining the conversation. And then we have machine translation, converting one language to another. And then report generation is really given a different modality, let's say an image or some graphical tables, can we generate a report from it, providing the key findings. So some specific NLP algorithms that I wanted to have a look at that I wanted to cover primarily is we'll be utilizing it in the second portion of it in the examples that I prepared. So the first one is a bag of words. It's a way to represent text. It's very easy and standard way of quick and standard way of representing a specific text. All it is you generate a vocabulary, which is all possible words within your data sets. Again, this could be tuned a bit so that you can limit it so that the number of frequencies can be a cutoff point as well. But bag of words just counts the number. You provide a representation of a given text based off its frequency. So given this example right here, it was the best of times, it was the worst of times, and we have in the last sentence the best. So if we consider this our data sets, our vocabulary will consist of it was the best of times and worst. So a vocabulary will consist of 7 words, and for each text, we count the number of words we count the number of words for that specific word. So in this case, it has one instance within this text. Was the best of times all have one instance, so they would have a value of 1. So this to represent this specific text in a bag of words would be a vector of 1, 1, 1, 1, 1, 1, 0. Vice versa. Similarly, it was the worst of time will have vector representation of 1, 1, 1, 0, 1, 1, 1. So we just generate a vector with the same length of as our vocabulary, and each element in the vector represents the count for that specific word. Now, there is a problem with this type of representation is the representation can get a bit skewed in the fact that we place a lot of weight towards highly frequent words, which may not provide meaningful information, specifically for classification. So an example would be highly common words such as the, in this given example, where the can appear in a given text multiple times, increasing the count. However, the is not really a good word to distinguish between the different sentences, just because it appears it appears way too often. So that's where TF-IDF comes in, where it's very similar to bag of words. However, we kind of can take in consideration these highly frequent words that may not provide much information when it comes to distinguishing in terms of for classification or sentence similarities. So the way TF-IDF works is we first calculate the term frequency. So that is the number of times the word appears in the given document over the length of the document. So so the length of this document is 6. And it appears 1/6. I actually noticed a minor mistake, so I'll update this slide before I distribute it to units to be distributed to all of you, where this specific document, the document length is not size of 6, it's actually length of 2. So all these should be a 0/6, 0/6, 1/6, 1/6, and so on and so forth. So that's the term frequency. And the inverse document frequency is the log of the number of documents over the number of times the word, the number of times the number of documents where the word appears in. So in this specific example, it appears in both this document and this text as well as in this text. So the number of times it appears, the number of documents that it appears in the documents is 2 times, and there's 3 documents. So what this will do is, if we look at a highly frequent word, such as uh, the, in this specific instance, as well as I noticed this should be adjusted as 3 as well. So I make those modifications. So if we notice here, the is a highly frequent word. It appears very often. It appears actually in all the documentation. So the log, this would be equate to 1, and log of 1 will equate to 0. So this representation for the would always be 0 because it wouldn't provide much value when it comes to for the classification, as well as distinguishing between these documentations. Another algorithm that I wanted to review is stemming and lemmatization. It's a form of way to normalize words to their root words. Um, I'm not going to go into the specific algorithm, the specific implementation of the algorithm. However, they perform very slightly different in the fact that lemmatization actually tries to uh, calculate its root word based off of its semantic meaning. So leaves will actually move towards the lemmatization to its root word of leaf. Whereas stemming, what it really does is really a pruning technique where it just removes postfix characters to try to gain a root word from it. So there, we do actually see that lemmatization might perform better, and this will perform better. However, in most cases, actually, lemmatization provides very little boost when it comes to the overall performance of the specific NLP task. So in most cases, it's good to try to incorporate lemmatization. However, I like to start off with stemming, and if the performance of stemming is fairly good, it might not necessarily be required to move to lemmatization, partly because the implementation for the performance of lemmatization um, decreases compared to stemming. So there's a trade-off between the performance as well, performance and the computational, accuracy performance and computational performance. So now we look at deep learning. Specifically, there are three common areas, three areas of deep learning: supervised, unsupervised, and semi-supervised. Supervised is the easiest tasks working when it comes to deep learning, primarily because um, you can dictate your model to learn the intended target output because the dataset contains the labeled data. So the model is able to correct itself based off of known information, the known expected information. Unsupervised is harder than supervised, where we have the data set contains no label at all. So the expected output of the data is unknown. However, in some cases, unsupervised is reviewed because unsupervised is um, the primary type of deep learning that's applied, in the fact that it's in some cases the problem task, uh, the labeling of the data set is unfeasible, and in deep learning, um, a large volume of data is required to gain good performance during training. The second option, the third, it being semi-supervised, in terms of difficulty when it comes to learning, specifically deep learning, it falls in between supervised and supervised. This contains a mixture of labeled and unlabeled data. The common approaches towards semi-supervised is utilizing the labeled data to train a model such that the, the that model can then be used to label the remaining data sets. The other very common approach to semi-supervised is to use the non-labeled data to gain a rich representation of the features, and then use the labeled data for the specific deep learning task. So the general architecture for deep learning, we have the input, hidden layers, and the output. The input as well as the output, the number of neurons, which are these units that perform the operations, it can be different between each layer. So the input can have a different set of number of neurons, different from the hidden layers, as well as different from the outputs. Similarly, the output can have a different number of neurons compared to the hidden layers, as well as the inputs. In addition, in the hidden layers, for deep learning, we can have a variety of we can have varying lengths of hidden layers, and each hidden layer does not necessarily have to have the same number of neurons, which we will see in the example that we go through. Uh, and And when it comes to the the general architecture for neurons, we have the feed-forward network, which we show right here, where one layer is sequentially feeds into the next. Next type of architecture we can have is recurrent neural network, where um, the outputs of a layer feeds back into uh, feeds back into a prior layer. So when it comes to deep learning, um, how deep learning learns, or in general how neural networks learns, is the very first iteration is what we call the forward pass. What that does is we feed in the input, and we have the neural network generate the output. After the feed forward, we calculate the loss function. What that entails is we compare the predicted output to the intended output, and determine how off our model was at predicting. Then, given the information of our loss, um, we go through the back propagation. What the back propagation does is, based off of um, the loss function and the gradients of the loss function towards the weights, we calculate how the the weights in the neural network should be adjusted. So that's the end of the presentation. Does anybody have any questions thus far? Okay. So if there's no uh, question thus far, I propose we take 10 minutes break, and then we can jump into the application example. So I currently have 6:50 p.m. Let's say we reconvene at 7. And looking at the chat right now, thank you, Ernest, for pointing that out. Yeah, yes, I did forget an M in stemming. I'll adjust that as well. Hi, everyone. Okay. So I think we can go ahead and begin the application portion of this workshop. So right now, first I just want to um, go over Kaggle and look, kind of show how to navigate through it. So at the top left, you have all your tabs. You have your compete data, notebooks, discussion, courses, and more. Um, if you want to host your own competition, you can go ahead and do the in-class competitions and then create new competitions. There's documentation specifically how to do that. You just need to enter all in the fields, upload your data, as well as determine your evaluation metric, and upload the solutions, the expected solutions. Again, as I mentioned in the data set and the notebooks, there's a large repository of notebooks that you can analyze and review. So if you find one that you really like, you can go ahead and actually make a copy of it, and that allows you to play around with it. Another thing with a notebook, you can create a new notebook, Python, notebook, as well as add an accelerator, um, accelerator to it. In order for you to add an accelerator, you just need to link a number to it, a number to your account. That's just Kaggle's security feature to ensure that a user does not create multiple accounts and abuses the free resources. Again, you can choose from Python and R, and you can choose the interactive notebook or just the script. So let's go ahead and create one. What you can do is, so it's very similar to the one, Colab. However, in this case, the data, you can upload it through here. So you can add a data and you can upload your own data sets, or actually look at one of the publicly available data sets already, or the competition data. So search up sentiment analysis. So specifically, we can actually look at this specific competition and review the description here and get details from the data. So we will kind of be looking at our example today based off this data sets, the Rotten Tomatoes data sets. It's a data set containing different phrases of movie reviews, and they're labeled based off sentiments in 5 different categories, being negative, somewhat negative, neutral, somewhat positive, and positive. This data set was originally created by Stanford. However, Kaggle cleaned it up slightly by removing duplicate entries, um, and duplicate words. This data set is just tabbed eliminated for that example. Another thing you can do when it comes to the Jupyter, the notebook specifically, to compare to uh, another thing you can do is upload a specific notebook based off of one that's available online. So as I mentioned, in the GitHub repository that I created for this workshops. We now have, I uploaded this session's material, and this is the example. You can get the URL and load it that way. So you can interact this way. One thing to note when it comes to the kernel is you can generate outputs. However, these outputs do not uh, persist towards the next session. You actually have to commit the notebook for those outputs to be persisted through a different session as well. Another thing I wanted to note regarding the notebook, if you are going to use Kaggle notebooks, is there is the utilization, the limitations for the Kaggle usage is based off time. So one thing you want to do is to make sure, especially when you're working with notebook and an interactive session, is to stop the session before you close the window. The reason being is if you close the window prior to stopping the session, the notebook session is actually still running, and it will continue to run until it hits the 60-minute idle time. So if you close it without stopping, the time between when you close the window to when you hit the 60-minute idle time will count towards your usage. So there's that. Another thing I wanted to note when it comes to the Kaggle, specifically with the Google Colab, is when you want to access data from Kaggle remotely through the API, you need to generate the API key. So what you do is you would click the top right corner of the icon and go to My Account. And then under the API section, you want to create an API, a new API token. That will download a JSON file with your specific API token. And you just use that JSON, load it to the environment that you're going to connect Kaggle to. So in the specific example that we're going to go through today, I'm going to go back and use Google Colab. So I actually created a folder in my drive, Kaggle, and API key within that folder. And within the given code to download, so again, we would need to mount. Oops. So we can mount our driver. To mount the driver, we're located to our Google account. You need to allow, and you're given some authorization code. Here we go. Once we're mounted, we are now mounted. If in your own Google Colab, I already have all the data sets downloaded, which is the sentiment analysis movie data sets. If you don't have it downloaded, then you can just uncomment this cell and execute this. What this will do is perform the mounting as well as download the data sets from Kaggle. However, one thing you want to make sure is to place your API Kaggle API key within your endpoint, the location, that's this line right here, where that API key is located. So you would have to adjust this to the specific location where your API key, the directory your API key is located in. So again, just to recap the sentiment analysis data sets, we have labeled 5 labels: negative, somewhat negative, neutral, somewhat positive, and positive. This line of code, I'm just loading in some necessary packages that we will be using to do some initial analysis on the data sets. Again, uh, you would need to modify this root directory to point to the specific location data set. If you followed from yesterday's session, as well as executed this cell block, it should be the same. However, if you decided to use a different directory, then it would be slightly different.
Sorry, Alex, can I ask for you to zoom in a little bit, if that's okay?
Oh, yes, no problem.
Thank you so much.
Yes. So there you go. Is that clear to everybody? Or should I zoom in a bit closer?
I think it's fine on my side. Yeah.
So the data set that I'm using is the sentiment analysis on movie reviews. So that's if you go to compete and just search up sentiment on the competitions, it should be the sentiment analysis on movie reviews. So this is the data sets. However, you will select the proper data sets if you're using the Google Colab, in the fact that this is the specific command to download the data sets, and it lets this is specifically pointing to that specific data set, the competition from the sentiment analysis on movie reviews. So there's that. Executed that. So this is just some cell block to adjust because my settings for my Google Colab is a background. So I just adjust some of the figures that I generate to have white text so that they're more visible. This is similar to what we did in the first session, is loading in the data set through Pandas data frame. And then train.head. So again, we can visually see what the data set looks like. So the data set, the trained data set, contains 4 columns, one being the phrase ID, the sentence ID, and then the specific phrase and the sentiment. So oftentimes when we work with NLP, with sentences, we work in we can actually get increase our data sets and provide more training data points by permutating one given sentences. So in this example, we have one full sentence, a series of escapides demonstrating the adjectives that what is good for the goose is also good for the gander, some of which occasionally amuses, but none of which amounts to much of a story. So if you notice, the other phrases from the sentences are just a portion of it with slightly different labels. So we can actually generate more data samples by generating permutations of a long text into smaller subsections of it to give us more training more training data points during training. And then our test data sets, of course, our test data set, we do not have the given labels. And then it also provides, in most competitions, it provides you sample formats of the sample format of the submission file. So in this case, in most cases, it's going to be something very similar to this, where you have to provide some form of file, oftentimes a CSV, where one is the ID as well as the intended label. So the IDs come from the test data sets, and in this case, the sentiment is what our model would predict. However, the sample that they gave us, they entered all twos in here. So one practice that I like to do when starting a competition specifically is generate a line of code that prepares that prepares the submission file. And at the beginning, it's really I generate a submission file by reading in the test file and just randomly generating labels for it and submitting that just to make sure that the submission process pipeline is working correctly. So again, we can look at some initial plottings to see the distribution of the labels. For this specific data set, we actually see an imbalance of the distribution of the labels, where we primarily see, I would say, more than half of the data sets are labeled neutral, and then there's an equal distribution between partly negative and partly positive. And then again, a similar equal distribution between positive and negative. However, we actually see a decrease of those samples. So oftentimes you want to distribute, you want to make your data set balanced, specifically, especially during training, to make sure that your model does not learn, is not biased towards that majority distribution. So there's different techniques to sampling. I did not provide one here, but I think it would, because I provided, I think it might be good exercise afterwards for you guys to try and implement sampling, some kind of balancing algorithm to take in consideration the unbalanced data set and compare the performance. So now let's look at some of the points that we kind of discussed earlier with regarding bag of words, specifically the frequencies. So in this set of codes, it's just generating some visualization so we can kind of visualize, manually visualize to see what our predominant words for each label is. So if we see in the positive case and the somewhat positive case, we should kind of see some similarities with some words. Fun is kind of somewhat similar. We have funny, funny, performance, performance seems to be a common term between these two. So there's a lot of frequent words that's actually being utilized uh, in all labels. So that would kind of indicate that these words aren't really good candidates to distinguish the text between these specific labels. If we can see movie, 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 it's highly frequent in all label sets. So a lot of words actually we can kind of see. Uh, they're very common words when describing a movie, regardless of the sentiment that you're applying to it. So we can actually take care of that by using stop words. So what this line of code does is review that data set, redisplay it, but remove those common stop words. You remove First, we utilize a default dictionary of stop words. Those commonly contain stop words like the, it's, very common within the English language. And then as well, we update that stop words to incorporate some of the common words that we saw across all the across the different labels. So we can actually now this gives us a little bit of better information. We actually see some words that's still not very good with distinguishing specifically the two polar opposites of the negatives area as well as the positive. So we actually see time and time being commonly used within the somewhat negative and somewhat positive. However, there does seem to be some indication that the frequency of words might yield some benefits in terms of distinguishing these polar opposites. Specifically, we see high frequent word bad being used in negative, where we don't really see that in positive. So that's really a good distinguishing factor, uh, even specifically just within this area. So actually, if we were just looking at a 3-level labeling task, this might be good enough where bad and bad is both within this realm of negativity, but it's not present within this realm of positivity. And so this section of code, we do some data preprocessing. We generate some initial key import libraries. In most cases, I find that these are very common preprocessing steps that occur in any NLP task. Uh, Depending on specific tasks, specific libraries actually yield better performance. But for this one specifically, I just decided to use the popular NLTK. So the pre-processing stages that we really do is we convert all the phrases to lowercase, removing non-alpha characters, as well as doing word tokenization, and doing stemming, specifically using snowball stem. And this is the process of doing that for the train test data set. So while we let that run, I'm just going to discuss the next component, which is splitting our training data sets into training and validation. In some instances, specifically in some instances of competition, they would actually provide you with a training, validation, and testing set already partitioned. In some cases, they'll give you training and testing data sets where you're responsible to partition the training data sets into training and validation. And in some cases, you're only given the training data sets, and you are required to provide your code for performance evaluation on a private data set. So again, so this has finished. We see that our pre-process, we remove some of the punctuation, as well as converted everything to lowercase. And there was some stemming that we see that was performed, specifically series got stemmed to seri. So to split the data sets, a very popular tool is to use the train test from the scikit-learn library. And all you have to do is pass in the input features, the labels, the split ratio. So I'm going to generate 20% of the training data set will be partitioned to validation, and 80% will remain as testing. And we specify a random state so that when we rerun this execution again at a later date, it performs the same splitting results. And then in this portions, we need to convert those texts into some type of representation that our model can understand. So just to recap, the models aren't able to process raw text. So we need to provide some numerical representation for it. Specifically, in this case, we're just going to use a bag of words. So well, we use the count vectorizer. What that does is you can specify the minimum of the frequency to be included in the vocabulary. So in this case, we're only considering words that have more than 5 or more occurrence within the whole data sets to be added in our vocabulary. There's other parameters that you can also look at. Another one that might be useful is the max features, or the max features that limits your vocabulary size to that specific dimension. Then we just perform fit, and that will do is generate the vocabulary list for us. And then what we can do is do vectorize that transform to actually vectorize the given text. So in this case, we do that for the train, the val, and the test. And this is an example what it occurs. So one thing to note is when we perform the transformation, this actually returns as a sparse matrix. Sparse partly because majority of the entries, it's a very large vector, as well as actually it's a very more large tensor with majority of the entries being 0. So the next portion is our example for the neural network. Again, we use PyTorch to implement our neural network. We just this section of line code performs the necessary imports for PyTorch. We defined just a feed-forward neural network. This is slightly different than last week's example in the fact that in this week we make the model a bit more dynamic in the fact that we can specify the input dimension as well as make it dynamic in the number of layers, the number of hidden layers that we can create for this model by passing in neurons. Neurons is just expected input for neurons is an array with indicating the number of neurons at each layer. So I defined it here. So in this specific example, I create a multi-layer perceptron with 4 hidden layers, where the first one has 800 neurons, second one's 500, 300, and 200 for the subsequent layers. Again, just to recap, when you create a neural network model, in the initialization, we define the structure of the structure of the network, so all its components, and then we also need to define the forward pass. Forward pass so indicates how input is fed through the system and how it maps and how it goes towards the output. If you notice, we actually don't need to specify the back propagation, and the reason behind that is because PyTorch uses autograd, so it calculates backwards gradients based off the forward pass coding. Another thing we define is the review data set. In PyTorch, you can define a custom data set. All you need to do is provide the initialization, provide the length, so how to calculate the length, the size of the data sets, and how each specific element is retrieved. So a data point in the data set is retrieved. So in this specific data set, I specify custom data set review data sets. I feed in the features as well as the labels. And for each data point, I extract the specific row entry for the features and convert it to array, because this, if you recall, when we process our input, when we do the vectorization, this returns us as a sparse matrix. So we want to convert it back to NumPy and flatten it out. And of course, we specify the matching label towards it. And then this line of code just checks if we have the GPU enabled. This line of code defines our model as well as our optimizer and our loss function. And then while we wait for that to load, we define here, we actually create our data sets for the trained data sets as well as the val data sets, and then load them into data loaders. What the data loader will do in PyTorch is make it easier to generate batches. So oftentimes we want to process data in batches for performance, as well as in most cases, in a lot of cases, computational restrictions will not allow you to process the whole data set at one time in one batch. In this line of code, I just run through one line, one epoch iteration, and feeding in the data and training the model. Oh, I forgot to load this, execute this cell block. And there's that. So while we wait for that, this line of code performs evaluates the model based off of the validation data sets. If you notice, the codes are very identical towards training as well as validation. The key difference is during validation, we don't want to enable gradient because we don't want to update the weights of our model, as well as in validation, if you notice, we actually don't do calculate the backward loss, calculate the gradients. That's through the loss step backwards. And then we don't update the weights because we don't call optimizer.step. So those two specific instructions are missing within the validation. So right now we're kind of reporting the cross entropy. Right now we only done one iteration. So our performance isn't really that strong, as well as our approach is very vanilla in the fact that we are doing, we did some feature engineering in the fact that we encoded our representation to be specifically TF-IDF, as well as we did very limited pre-processing. So there's a lot of room for improvement to generate a lower loss function. However, I thought this might be some good exercises for everyone to try. One being to balance the data set and see how the model performs. Try TF-IDF, incorporate additional pre-processing, as well as play around with the network architecture, and then possibly incorporate incorporate some additional evaluation metrics, maybe some accuracy or F1 score, as well as very common one, very easy one to generate higher performance for this example is update the code so it runs through multiple epochs. So that is the end of the application portion of the workshop. And in addition, also ends the work, this session. Does anybody have any questions that I can answer?
Yes, I was thinking, like I haven't run this yet. I want to give it a try
Yep.
later today or this week. But I was thinking whether this method and like the data sets that you're using here, what if the contents were not English or written in like a language where the characters are the same as English, like an Arabic or something?
So there are packages that support different languages. In terms of the pre-processing, it really that comes down to the pre-processing part, where if you want to do some of those things when it comes to different language, there it is, different packages have higher support for multi-languages. Some have a niche specific language that it supports that others don't support. So there's that component. However, when we it's really comes down to the pre-processing, as well as there is it's also not necessarily. So if you're working with, let's say, sentiment analysis, and you got really high performance with the English language with a specific model, it might not necessarily be transferable to a different language. So if you use that same model, train it with with the specific language that you're intended to, it might not necessarily yield the same results, in the fact that different languages have specific different linguistic rules. So that's
like
one
the
thing.
lemmatizer, finding the lemma or this.
Oh, so yeah. So really, when it comes to other languages, that's the biggest components. Really, that biggest challenges. Not really biggest challenges, but one of the challenges in the fact that really depending on the language of your given choice, um, the package might not support it. The package. So lemmatization, again, lemmatization. The one that I use is NLTK. I'm not sure at the top of my head which languages it supports. I know NLTK has a very large repository of languages it supports. However, uh, there's also other packages that also do lemmatization that may have that specific language supported.
Okay.
Yeah.
Thank you.
If it's not available, then you would have to implement that component.
I understand. So just to be sure about like the example you gave here, apart from the stemmer and like the lemmatizer, are there any other component that is language specific that you can point to in this process that you presented today?
Really, that's really highly dependent on the language. Would be the only areas would be in the pre-processing, like removing alphanumerical letters. Again, if if uh, the for that specific language, if it uses Sanskrit, then this line of code won't work, essentially. As well as if you're looking at a language that uses letters, but there is hyphens in those letters, this might remove those hyphenated letters.
I understand. And
Yeah.
quick question though, are we doing any treatment of the subject of machine translation in this series of workshops? Like doing anything in PyTorch that, you know?
No, so machine translation, I did not want to cover that component because I'm thinking potentially an advanced continuation of this course for that workshop, because um, machine translation has a component of natural language generation, and that itself is a large topic.
I understand.
Yeah,
Thank you so much. Thank you.
yeah, yeah. Okay. Any other questions? Which activation functions are supported? Um, so the very common activation functions are supported in PyTorch. We have the sigmoid, we have the relu, we have the tanh. So let's see all the activation functions. They're all available on the repository. Sorry, the documentation for PyTorch. However, the great thing with PyTorch is you can actually create your own activation function as long as um, your your custom equations are differentiable and it won't break the graph, the computational graph. Okay, so we're over time, so I think if there's no more questions, I think we can end the session. Any closing remarks, Eunice?
I'm sorry, I think for a second my microphone, I wasn't able to unmute it. No, thank you so much. As always, I will send the video as well as the slides in a few days to everyone.
Okay. And thank you everyone for joining. Again, Eunice, I'm also going to send the link towards just the Google form for just the survey
Sure.
for this session. And if participants can fill it out, that'd be very much appreciated. So we can fine tune really this workshop.
Yeah. Thank you so much.
Okay.
And I hope see everyone next session as well.
Yes. Thank you.
Bye now.
Bye-bye.